geht aber heute weniger um mich, es geht um den lieben Hendrik. Er ist Netzwerker, er ist Feuerwehrmann und er ist eigentlich auch so ein richtiger WLAN-Nerd, wenn man das so sagen kann. Und er betreut 1600 Access Points, übrigens auch die ganzen Access Points hier im NOC. Dafür mal vielleicht noch eine Runde Applaus. Also die ideale Voraussetzung, um uns heute zu erklären.
Hello, dear listeners. Welcome to this talk on making Wi-Fi fast again. This is Oliver and Ralf from the translation team. If you have feedback to the translators, tweet C3Translate or use the hashtag C3T or email us at hello@c3lingo.org. The speaker today is a Wi-Fi expert who has more than 1,600 access points in operation, and he's going to talk about all sorts of Wi-Fi magic today. So please let us welcome Hendrik, our speaker. Yeah, hi. Also, hello from me and welcome to GPN in winter. It's very nice to have you all here. I just heard a boo in terms of Wi-Fi with NOC. We had a small problem. We made Wi-Fi even faster before this talk. And so things had a little hiccup for a while, but now everything should be working again. So the structure of the talk today is I'll start talking a little bit about me. I didn't actually expect somebody to introduce me. Some details for the history of the Wi-Fi standard. How did Wi-Fi develop? When did it come? How long does it exist? A little overview over what changed with IEEE 802.11ac, which is the full name of the standard. What changed with this new standard? So then we go more into detail. What changed on layer 1 of the standard, the physical layer? Because that's really what makes it possible for the higher throughput to appear with the standard. Then I will understand what is this MIMO and this multi-user MIMO. That's very interesting, because this again gets us more bandwidth. Then I will go into this magic beamforming that maybe some of you heard about already, which you can do with high frequency waves, but also with audio, for example. And in the end, I will do a little, relate this to praxis and reality. How useful is the standard in practice? What does it get us in reality in terms of throughput? And then a slight outlook on the future, because IEEE didn't stop working. They are already working on the next standard, so we will see what is coming there. So I'm Hendrik, 23 years old. I'm studying in Karlsruhe at the Institute for Electrotechnology. I'm helping out there with the network. I'm responsible for 1,600 access points, and I'm responsible for setting up the controllers and the installations of the access points in the lecture halls, so that in halls like this, Wi-Fi is working properly. And when I have some free time, I'm also doing amateur radio and some little playing around. So some little history of 802.11. So this started out really early. They stored cables, that's really nice, but now we can build laptops. And now already putting your laptop somewhere and plugging in a cable, that's really annoying. Putting the cables everywhere in large cables, that doesn't really work. So at some point they started thinking, okay, let's do this without a cable. Ever since then, they, in regular intervals, they release new standards that each time improve Wi-Fi in some sense, maybe there's higher throughput, or more generally speaking, more efficient Wi-Fi in general. That's the timeline of Wi-Fi here. It started in September 1999 with 802.11a and 802.11b. Those were the really old and slow data rates, 11 megabits per second. Compared to nowadays, that's really slow. Back then, the idea was just let's have something without a cable and get some data through it. And back in 1999, 11 Mbit was actually quite significant, because back then 16 megabit DSL at home, that nobody had that. It's not like the DSL speeds we're having today. Then 802.11g was released in June 2003. And then more and more standards appeared, which went further and further in terms of optimizing data throughput and efficiency. Like, for example, with 802.11g, which maybe you know from your WRT 450 GL, which could actually do 54 megabit via Wi-Fi, which actually is really cool. And then Fritzbox came and said, oh, I can do 300 megabit. And that way, standards progressed. So also in the 5 gigahertz frequency range, which we have today, that already existed back then in 802.11a, the A standards. That was the first time 5 gigahertz got into the game. The problem with 5 gigahertz is, through the higher frequency, the signal is damped more strongly through humans or walls. So actually using this to cover a larger area is not really working so well, which is why back then 2.4 gigahertz was preferred and focused. Because that gives you a higher range, which was more important back then compared to higher throughput. Then we got 802.11ac as a latest milestone, which was 2013, released after quite some work. So as a summary, I have to say that the 802.11-2007, which appeared in March 2007, that's not really a new standard. It's more like a summary of all the existing standards and extension prior to that. Because that IEEE standard is being submitted, and then all the additional things, all these additional letters, A, B, G, A, everything, was just extensions to the basis. So in 2007, they decided, let's just sum this up already so that we have like a base standard again in one large block, so that it's easier to read. And if you look through the 802.11ac standard, you can see that half of the pages is just striked out, and then there's some little things added, and some things are in italic, and it's really just a huge patch for the previous standard. And layering all of these standards on top of each other to build something is really hard, which is why in 2007 they just summed it up all in one block. So 802.11ac is always being called this gigabit Wi-Fi, and everybody is happy. I can still remember at CeBIT, AVM made advertisements. We can now transmit 1 gigabit over the air, and I was like, wow, that's really cool. However, the standard is only specified for 5 gigahertz because people said, well, 2.4 gigahertz, we only have 4 channels which you can use effectively without having an overlap. So let's do this 5 gigahertz only, which is enough, and that makes our job much easier. But then there were additional ways of modulating the wave were picked, which are more efficient, so they can transmit more data per time. Because, for example, with one setting of the modulation, I will talk more about this later, more bits can be transmitted. We have wider channels, because if the channels are wider, then we can send twice as much data because we have twice as much frequency range for the same time. There's fewer MCS values, which stands for modulation encoding scheme, which is an index saying which kind of modulation and bit redundancy, bit security is used. If you just transmit data, you can just transmit it, but you should really expect that your transmission is somehow like there's loss on your transmission, and to compensate for that loss, you take some of your payload data and add an additional bit or another kind of checksum after it to make sure that actually really everything was transmitted. And these MCS indices are a combination of the modulation and the way that the bits are secured and probably made redundant. What's also got very interesting is that this beamforming was specified more precisely. In principle, beamforming already existed with 802.11n, but there were many different beamforming methods, and every manufacturer had their own beamforming method, implementing whatever they liked most, and not all clients supported it, and there were problems with clients from one client interacting with access points from other clients, and when they tried to do beamforming. So with this one, they went ahead and said, well, okay, that's exactly what we're doing now. And then, as already mentioned previously, multi-user MIMO is coming with 802.11ac, which will make us like lots of fun. And finally, they said that, well, we got 802.11n. With 802.11n, they made a mistake. They defined a standard which was huge. It encompasses, compared to the 54 megabit, the 11G, which was 11G dude, 11n just had way too many things that were added, new frequencies, and many other things, and manufacturers just were not able in the short time to properly implement the standard and the hardware and provide the hardware. So what they said is, well, okay, this time we're going to have 2 waves. So the first draft version of 11AC, when it was released, they said, this is wave 1. So manufacturers can start producing it, and we will guarantee that the part which we released won't be changed in ways such that you will have problems with like incompatible clients or that only support the latest version, for example. And with the second wave, that was when the standard was really done. That was 2013, and now that's actually the final thing.
It got interesting with respect to data throughput on the physical layer. That is which limits us in the most cases. Modulation modes and channels. So they decided on more channels, because now the access points don't collide with each other. On 2.4 we can use 4 channels without collisions. So now we're using more channels. We're also using wider channels. This increases the throughput fantastically. So there's a 3-to-3 MIMO, which is being advertised on routers as the number of aerials normally. FAC has defined it, and they have defined that there can be up to 8 separate independent transmissions on the same frequency. So now we have the 8 times the data throughput. Multi-user MIMO allows simultaneous transmission to multiple users. We use separate transmitters inside the access point and channel them to different users. We have an improved modulation encoding set. And this reorganization of how to do the modulation coding gave them more options. This diagram shows all channels that are available. Not everything is permitted. And they looked at 5 gigahertz, and then they found there's weather radar. And then they found that they have to do dynamic frequency selection. They have to check, is there a radar? And if there's a radar, then we better not do anything. The access point has to retract from the channel and use something else. In Germany, the restrictions are even further. There was great legislation of what was going to be inside the standard, and the regulatory agency, both in Europe and in America, has added further restrictions. This shows the maximum possible. And they are fighting for the gray stuff, which I can't see. So if everything is possible with and without DFS, that would be the maximum. But it doesn't work everywhere. The channels can overlap as in previous wireless LAN standards. This gave more options to avoid collisions between access points. Changes, improvements in the physical layer The MIMO has been in existence since 802.11.n. It is, if you use 3 aerials, then you can use them simultaneously. The physical separation on the aerials allows for differentiation of different strength of signal, and the differentiation of strength of signal allows for different channels. One could call it a channel. Anyway, it increases the data throughput. There's one data stream per aerial, and it allows parallel transmission on the same frequency. I will bring a table in a moment that shows what the 8 partial streams give us in throughput. After the reorganization of the modulation and coding sets, they said it was too much, and they found that not all of them were used equally. We can build better hardware, so we don't need all of them. So they restricted from the large number of coding sets to a lower number, and they have a higher data throughput. So these modulation types are available now, and here are the improvements. The improvement is quadruple amplitude modulation is the QAM, and the 256 ones are new. The code rate shows how many bits are redundancy or error correction. At the bottom, you can see that half of all the bits are used for protecting the data for long-range transmission. In other cases, they say we can omit the error correction, and we have a very good physical conditions, and we don't need it, and we can use it for throughput. Quadruple amplitude modulation is a digital modulation, a form of modulation, and it is a combination of phase modulation and amplitude modulation. The I and Q stand for the phase and amplitude. Und genau diese I- und Q-Werte sind diese Werte, die für eine QAM-Modulation notwendig sind. So exactly the I and Q values are what are necessary for the QAM modulation. This combination can be identified clearly in a big grid, and therefore represent the associated bits. It depends on how you cover your grid with a bit pattern on how they are mapped. On one frequency, we provide a small carrier signal, and then we add lots and lots of modulated carriers. The receiver checks, this is what I've received, and I use the unmodulated carrier as a reference. And then I compare the phase and amplitude to the unmodulated one, and that gives me the number. In higher frequencies, we need extra carriers, because there's a phase shift in higher frequencies because the frequency is higher, and the wave has progressed further already.
The 64 in the QAM is short for the number of modulation points, the number of points we have in this grid. So this is how, for example, the grid of a QAM 64 could look like. I is for the in-phase component, which is the phase difference of the entire thing. And Q is the quadrature component, the quadratic component, the 90 degrees angle to the phase. So with 64 values, we can encode 6-bit per configuration point. So if we, for example, use the gray code, which we can just overlay over this, or other encoding methods which you may want to use. So for example, the 256 QAM uses, which is used with 8.2.11ac, uses 2 times 4-bit gray code, which means that we got 8-bit that are concatenated, and the first 4-bit are gray code, which is like using the X directions, and the remaining 4 bits of the code word are gray code, which is oriented in Y direction. The discussion for how to add gray code on these grids can be extended arbitrarily. I recently had a very nice discussion with a roommate over this, over breakfast. If you can, in an n-dimensional space, we have m constellation point for every one of these n dimensions, and you can have a gray code for every dimension. How long is the code word, and how many bits y are added with the n to n plus 1th dimension. And she threw all sorts of mathematics on top of this. It's possible to do this in the n-dimensional, but that doesn't really matter for us, because we first have to find a third parameter for the space to even use this. So I'm very happy with the normal QRM so far. This is a small example. Let's look at this short point in the top right corner. So I just counted from the beginning binary. I didn't add any gray code or anything. So if you want to have this point, that's the 15th point in decimal, so this is our decimal, our bit, or binary value here, that would be an x value of 4 and a y value of 3. So if my antenna now recognizes I got a phase shift of corresponding to 4 in the x direction, and an amplitude difference which corresponds to 3 in the y direction, then that's exactly this binary value. So that's how this is encoded. So this is, now we have a huge table. That's kind of not very nice to get an overview over this. It starts in the beginning with 8.2.11n with one spatial stream compared to 8.2.11ac spatial stream, with one spatial stream. So this table really nicely shows how adding more spatial streams, more possibilities for sending more channels on the same frequency, so to speak, how this increases the data throughput up onto 683 megabit. That's way more than the N standard was able to do in its maximal configuration. And you still have to add in defense of 8.2.11ac that these gray values, these gray values are not even using MCS index 9, they're using MCS 8, because the 20 megahertz channels, they must not be used with the MCS index 9. That has been specified like this in the standard, which means if you would look at it theoretically, which is not allowed by the standard, you could pump even more data through this. If we now widen the channel, then we got even more throughput. So then everything is possible again. And if we widen the channel again, then we get even more throughput. And that's the point where things start to have holes, because 80 megahertz is actually not something which was possible in 8.2.11n. However, we can widen again. We got 160 megabit channels, and then we get in the bottom right corner, we get the value which is the maximally possible throughput rate on the 8.2.11ac. That's 69 gigabits per second. And that's where I have to start thinking, how do I get my data to the access point? Even with some new standards where I can get 2 or 5 gigabit over my copper wire, even then that's not enough. So that was like really shooting very, very high. So specify 6 or 9 gigabit, well, let them do that, that's okay. And again, we have a blue value here. The MCS 9 is not specified is forbidden for values with three streams and 160 megabits for reasons which I don't want to go into here, because that's details in the standard and it's not interesting. So now this multi-user MIMO. we already have this idea of using the antenna to send multiple streams with the same data, which, if you think about this, that's already, imagine this, we have on the same frequency, we are sending multiple streams to the same client, and they are like somehow separated again. That's already a technical genius. And then they were like, wait, we can do that. We can actually do better. We got the MIMO with 802.11n, but we can go further. We don't just have like higher antenna gain, logarithmic in the number of antennas. For people who are interested in these details, but these people exist, right? I already mentioned by remote, right? So they went further and they said, we will do concurrent data transmission to all users that we see. And we do this just because we want and because we can, and then they did. So then they had to limit it slightly, so they said, let's do no more than 4 users, and let's not do more than 4 spatial streams per user, but there are no more than 8 spatial streams anyway. So this gives us some more advantages. For example, if we have a laptop which is pulling a lot of data right now, then it would, if it would be really close to the access point, it would be blocking the channel because it would be pulling all the data. And then other clients, well, at some point, they would also get their turn, but most data would get to the laptop. However, if you now sit there with 8 spatial streams and the laptop is using 4 spatial streams, well, it can do that because the rest of the client can use the remaining 4 spatial streams using multi-user MIMO, and so some smartphones can still get some push messages, which usually would not be sent yet, but they can already be distributed. That gives us some huge advantage, like for example for latency in the entire network, because smaller data transmission can just be thrown out there. That's really cool. So the best thing is you can actually pick a different MCS index per user. So we are sending, and we have the choice for every different user to use a different modulation, a different redundancy scheme. That's really a technical achievement where I sometimes think, how was this possible? How did they implement this? Building something like that, that's really something. So then there was this other thing, beam shaping. That's really cool stuff. Really, it's cool stuff. For example, in my hackerspace, they now built a speaker which uses beam shaping of audio, and it sends audio in just one direction. So something you didn't hear, I actually was somebody like has put the Nestle song on my ear from the side, and you couldn't hear it because it was beam shaped only into my direction. It's really just an active modulation of the dissipation behavior in high frequency range. So in 8.2.11 AC, this gives us an additional gain in terms of signal of around about 2.5 dB, because we can push our data exactly into one direction. And that's much better, because the further we are away from the access point, the worse our signal gets, of course. So we are sliding into lower MCS indices, and we can get less data. So if we can now amplify our transmission into one direction, that has the advantage that we can get more data pushed through this. So we have the advantage that we are finished with our transmission earlier, so everybody else also gets more A-time to use this network. Beam shaping, as all you already mentioned earlier, already existed in 8.2.11n, but there were so many weird things there, and now they finally agreed with 11AC, and it's actually possible bidirectional. There's hardly any clients supporting this, because most clients only have 2 or 3 antennas for 2 or 3 spatial streams. So there's not much support for this there. But in particular in the enterprise area, manufacturers started implementing this beam shaping, and it worked really nicely, but not for the uplink. It doesn't always work for the uplink. It's not always possible. So here I plotted this. I took the relative distance to the access point and plotted the MCS indices. The lower arrow is what happens when we use beam shaping, and the 2.5 dB gain, which we got, then we can be way further away from the access point, and we can use a higher MCS index, so we can get the same data transmitted in a higher distance from the access point, which gives us some compensation for the loss that 5 gigahertz has anyway because of the higher damping.
Now we're going to talk about phased array antennas. This is a space-efficient way of replacing a Yagi antenna. And if I have a very big antenna, then I need a motor and it needs to start and so on. It takes time. And the phased array can very quickly change the direction. And we can do this in this case. It is technically very cumbersome, but it is possible. We do this through a phase shift during the transmission. We have a number of antennas which are parallel to each other, and if we start sending the signal on one end earlier than in the other ones, then the whole signal changes direction to the side. And through this mechanism, the phased array is controlled. You need to compute an individual phase per antenna. You can implement it fixed on a board. So if you build a radar phased array in a car, then you make the wire to the one antenna longer than to the other, and that gives you a direction. And here's a picture showing how it works. This is the only picture I've taken from Wikipedia. There are no pretty pictures to this topic otherwise. If one of you guys wants to, if you want to load them into Wikipedia, then you can talk to me later and I'll give them to you happily. So they've decided on this thing, null data packet beamforming, and it really requires that you measure the channel before you do your transmission. Then you have to distinguish between the one who forms the beam and the client who receives the formed beam. And the terms are beamformer and beamformee. The angle of the transmission will be held in matrices. Matrices are better than angles. So we have two matrices. We have the feedback matrix, the one that we get back from the client on how he listens to us, how he hears us, and we have the steering matrix, which gets applied to our transmission in order to form the transmission. In the standard you can read it, but it is really painful to read. So the null data packet beamforming. You start with an announcement that you want to measure. Then you start sending 0 data packets. And now the client knows what the packet is, and he can measure the direction.
Und kann es sozusagen merken und sich als Feedback-Matrix, das als Feedback-Matrix entsprechend umsetzen.
And then the client computes a feedback matrix and sends it back. And then the master starts sending the actual data. And that data will then be received by the client. So since we know that IEEE are crazy, we're not only doing beamforming with one client, we're doing it with multiple clients. So we're doing multi-user MIMO and we're doing beamforming to multiple clients at the same time. So the technical implementation is very, very good. First, he sends an announcement that he wants to measure, then he sends the packet, and then he asks for the feedback.
Und fängt an zu senden. Ja. Das hat auch ein paar Nachteile. Natürlich diese Kanalvermessung kostet Airtime. Da kann
Measuring the channel does cost some airtime. And the size of the feedback matrix is different depending on the number of clients, depending on the number of partial streams of the clients, and some other parameters. The width of the channel is part of the determining factors. And this matrix can be anywhere from 78 bytes to 53 kilobytes.
Ja, hier nimm mal irgendwie. Also das variiert sehr stark. Deswegen
there's great variation in the size.
0,5 bis 1% unserer Airtime, wenn wir Beamforming machen.
So half to 1% of the airtime is for the measurements of beamforming consumed.
Und auch hier sind sie wieder erstaunlich genau.
They are surprisingly accurate. For every single subcarrier, they can apply 56 angles when doing 8 partial streams.
Aufteilen und in die Richtung drücken. Und das ist eigentlich, wenn man sich mal genau überlegt und auch auf die Geschwindigkeit.
So when you think about this and think about the speed at which the data is being transmitted, then this is a very accurate targeting. So now we are comparing the reality to the theory. And I love the standard, and it's fantastic. But unfortunately, the data rates in reality are slower. If you look at the access points around here, you will not get that much data through as the standard promises. There are two reasons for this. We have very many people in the room, and we have restricted how wide a channel can be.
Das Ganze hatte ich ja auch schon ausgeführt, warum man das auch machen sollte in meinem Talk auf VPN.
I have explained earlier why one should restrict the channel size. Then,
wenn irgendjemand von euch noch ein 2,4 Gigahertz Gerät hat, ne, und die Hände stehen beim Rausgehen.
So he's very unhappy about 2.4 gigahertz clients.
Aber es ist nicht nur 2,4 Gigahertz, es ist auch 5 Gigahertz, weil 11 AC ist ja noch 5 Gigahertz.
So he's also unhappy about 5 AC clients, the 11 AC clients on 5 gigahertz. He's also unhappy about because they also don't conform to the new standard.
Mit diesen Legacy Clients. Und hier auf dem Congress ist es sowieso schöner. Wir haben ungefähr 75% der Leute sind um 5 Gigahertz.
Here at the Congress, we have a very good coverage with modern equipment, and 75% of the people have the end standard. Broadcast will be transmitted with the lowest data rate.
Und mein Access Point sagt auch so, okay, das Niedrigste, was ich kann, ist N. Dann fängt der Access Point an, mit N zu senden.
So if you have a client and the access point negotiating, then clearly the lower one will be chosen. So if one of the two says it'll speak N, then the other one will speak N too. And then it takes longer. So the usage of 80 megahertz and 160 megahertz channels is very difficult in Germany. We are very limited to some channels here. The bands that we have allotted are very small and very narrow, and in Germany we simply can't find 80 and 160 megahertz channels inside those allotted bands. And that is a break that puts the brakes on our standard. There are problems with very high density deployments.
Leute das gedacht haben. Das liegt primär daran, einfach, dass dieser Standard nicht so vernünftig implementiert wurde.
So the implementation isn't always exactly as the standard prescribes it. So the manufacturers have omitted some things. They have not implemented beamforming unilaterally.
Die jetzt dieses Jahr zum Beispiel oder letztes Jahr rausgekommen sind, die jetzt hier irgendwie die ganze Zeit rumhängen, können das alle nicht.
The access points that we have here don't do beamforming.
Und das Ganze macht es dann natürlich auch nochmal ein bisschen schwieriger, weil wir auch wieder da auf schlechte Datenraten zurückfallen.
Makes it harder.
Dann hat auch dieses Ausrollen in Wellen eine coole Idee nicht wirklich funktioniert.
In addition, this great idea of deployment things in terms of wave didn't really work properly. Well, wave 1 worked, wave 2 worked, but then people thought, well, wave 2 is what we have to support at least, so that's good enough. So far, I've not found any client which actually supports 8 special streams. No standard actually supports the entire standard. I found a chipset which does this, but the chipset doesn't give me anything if I don't find a chip which I can put below this and then I can use this. The problem with this to some extent is the power supply. An access point needs power somehow, obviously. If we use power over Ethernet or PoE plus to do this, for example, that following 802.11.3 AT, that's roughly 25 watt. That's very cool. That's enough usually. However, if we now start doing spatial mapping, where we split the data stream onto the different spatial streams so that they can be put together back then, that requires a big digital CPU which can process all of this. The more streams we want to use in parallel, the bigger the CPU has to be, so the more power it is using. So that's unfortunately still a problem getting the power to the AP. So beamforming, as already mentioned, is not very widespread. Also, the uplink of the access point is by long extent not into the limits of the standard. Most access points have 1 or 2 gigabit, and now saw the first standard that actually support 2.5 gigabit for the uplink, but you don't need this. At the university, at our access points, we see maximal uplink usage of like 200 megabit. Also here on Congress, access points don't even remotely reach the limits of the standard. I have not yet seen a single access point which actually was able to get the throughput of a gigabit from the Wi-Fi to the LAN. That's probably possible in the lab, but of course when you have a Wi-Fi standard, it's not about the lab. It's about actually getting this in the wild, where there's actual people. So some people, for example, live in the city and not on the land, on the countryside. So where on the countryside, of course, you have all the frequency for yourself, but in the city, you're sharing it with all your neighbors. So and things don't work as well. However, I got some nice ideas. All of this has a future. Things have to be optimized further. IEEE is by a long reach not at the point yet where they are like, that's how we want it, that's how we want to use it, that's how everything will stay. So the hunger for more data throughput is not yet satisfied. We need better support for very high density deployments, like for example in rooms like this, where the access points and the clients, we have to make sure that they don't disturb and annoy each other so much. We have to make sure everything interacts with each other better. So to this extent, we have 802.11ax-2019. Yes, that's the new thing. If you think 11ac is sexy, you didn't see this one. It's again another huge step. So far, unfortunately, I wasn't able to get draft 1.0. If somebody has access to the IEEE drafts, I would look at this really. I would really like to look at this. My university does get the standards, but only the ones that are finished, not the drafts. I would really like to have this. I would really like to read it, because just looking at papers, you don't get the ideas. With this one, we get 1024 QAM, 2 more MCS values, much higher throughput. So it's going to be awesome. However, with this standard, they said it's not just about more data. Let's get some more data, but let's also optimize some other things. So this multi-user MIMO, let's do this bidirectional, so that multiple, not only the access point can send multiple data streams to different clients, that also different clients can send at the same time their independent data streams to the access point. That's really cool, really cool. And then we got OFDMA, which is for frequency-directed multiple access. That's a huge word. It's really complicated. Most of you have it in your bags, though LTE is using that. At the same time, multiple users can use the different sub-carriers of a transmission, and they get very weird, like nested access to the same channel. I plan to tell something about 802.11ax at the next GPN, where I will explore this further. I'm already almost using up my time here. So with OFDMA, everything will be much nicer, and I'm really, really looking forward to the standard. There's already the first chips based on the draft 1.0. So hardware developers are now very much invited to implement the standard. So this already brings me to the end of my short excursus. I hope it wasn't too boring. I'm very thankful that you listened to it, and now I'm looking forward to your questions.
Ja, wow. Toller Talk. Danke. Wir haben noch Zeit für Q&A.
We got some time for Q&A.
Wer schon gehen will, nehmt bitte den Müll mit.
If you want to leave, please take your trash with you, but we got some 10 minutes for Q&A.
Das Mikrofon hier.
The mic here in the hall. Question. Hello. You mentioned that the matrices, I think with the beamforming, the matrices are different in size. Is this because the matrices get more rows and columns, or answer is yes? Yes, I think that's because they have to contain more data, because from 8 spatial streams you have to specify more precisely what the angle is. So the individual values have more data. So that would be my question. The values get larger, or no? The answer is both.
Hier auf der Seite.
Mike on the side.
Willst du?
Yes, sorry for asking in English.
Yeah, no problem.
What is
Question is actually in English.
Angular resolution which you can get with MIMO with 802.11ac?
Yeah, if you take 8 spatial streams and you take your 360 degree and an antenna array which is placed in a circle, you just divide your 260 degrees through the 56, and then you get your angle, which you can reach with beamforming. Like, yeah.
Okay, wir haben eine Frage aus dem Internet.
So another question from the internet.
Wir haben hier 2 Fragen und ich würde die einfach mal zum einen erstmal viel Applaus auch aus dem Internet und dann
For once, lots of applause from the internet. So now the question from the internet. 2 questions summarized at one. How does much movement of the clients, how does this affect beamforming, like 500 people leaving a room at once? And on the other hand, is it possible to control this? Do you see more potential with beamforming to extend this? Answer: yes, I do see lots of potential with beamforming to extend this. For example, you could support more spatial streams, but then you also need more power. How does beamforming work when lots of people leave the room? Well, when all of these people like suddenly leave the room, I'm going to find you. Then in most of the cases, they won't just like run around and transmit data all the time. Beamforming does cost lots of airtime. However, in principle, beamforming is very quick. It doesn't even take like a millisecond to measure and transmit this. And because the angles are really are slightly wider, so it's still possible for the clients to move in this. And well, in doubt, it's going to be a error in the transmission, and they just have to restart. So at that point, it's really nice to have CCP. Question, disclaimer, I'm a software person, so all this hardware is just voodoo for me. So I wondered, how do you measure these things? How do you debug? How do you do troubleshooting? Answer, so what do you mean? What exactly do you mean? Question everything. Answer, well, measuring high frequency. So my professor says when you ask him how do you measure frequency, that's several lectures to explain this. To develop this high frequency stuff, you have to set it up in parts, compute everything, measure everything. So as a user doing troubleshooting, that's difficult. You have to rely on the chips that were used there to actually work properly. I know people that are now starting to look at the HTA 10K binary blob and reverse engineer it to fix the bugs in it and to figure out what is going on there and how things are working. If you don't actually have contact to the sources, then troubleshooting is really hard. Question? So what about this beamforming? In this 802.11 standard, I got I'm not allowed to send stronger than 100 milliwatt. So with beamforming, I got a 2.5 dB increase in power. Is this okay legally, if anybody would care? Answer, technically speaking, well, technically speaking, not. The access point would have to be careful. However, just forgot in this excitement. Another advantage with beamforming is if we have access points that one sends in one direction and one sends in another direction, the access points are not disturbing each other as much anymore, which is also another advantage. But looking at the legalese, yes, they would not be allowed to go beyond this in the transmission. So if you have a question, if you have a really annoyed neighbor, they could sue you. Answer, well, in principle, yes, but they will still have to measure this, and also it would be the manufacturer's fault and not yours.
In your frequency plan, you have channel 144 through 149. And what is the reason? Secondly, in the NTP announcements, are they sent isosynchronous, or which times are they sent in, and is it done on demand, or how is it done? Null data packet forming works in such a way so that they measure before every transmission, because the clients aren't to be expected in the same place. And when you are using beamforming, then you are expecting multiple clients. So it may be a very different client, and so you measure again. You were talking about the channels 100. The channels I'm interested in is 144 through 149 has a gap. The channels exist theoretically, but they were denied from the standardization. The regulator said this cannot be used. We don't know the reasons. It is not a legacy reason. It might be radar. When I made the picture in the train, I thought I have to explain it, but I haven't. I can Twitter it later, perhaps.
Okay. Letzten Fragen? Hier nochmal einen?
Ja,
Thank you for the talk. The raw data rate is one thing, but is there anything else that has been improved with AC that you should talk about? Yes, layer 2 of the standard has made changes and improvements, but I would need to show you packets and explain why there's a 1 and a 0 and why that would be an improvement. The difference of packets between 11N and 11AC would be too theoretical and boring for this talk here. I can recommend some literature on the topic. 802.11ac, the guide. The book is called 802.11ac, the definite guide, from Matthew Asgast. And he explains how these things work and how the packets are structured.
Okay, hier noch eine und eine noch aus dem Internet und dann...
One more question from here and one from the internet.
Jetzt hattest du AX. Ich hatte auch schon mal was vom Wireless AD Standard gehört. Ich glaube, das ist ja mit 60
You
GHz.
mentioned AX, then I heard AD.
4 GHz, Cloud im 5 GHz war Anti-Airtime, da würde ich...
Nee, das
okay.
das war falsch.
Does one of those standards steal the airtime of the other? No, it doesn't.
Irgendwann auch hostbasierendes Roaming enthalten. Soweit ich immer weiß, gibt
I have heard there's host-based roaming in one of the standards.
Roaming Standards in
Yes, there are roaming standards in 802.11.
allerdings, ich glaube, es gibt sogar 3 Stück.
I think there's about 3 of them.
Also richtig standardisiert, nicht die proprietären.
Es gibt standardisierte.
Yes, there's also standardized ones.
Die Anwendung und Funktion davon ist so ein Punkt. Es dauert natürlich immer, bis irgendwelche Standards drin sind und
It always takes time for the standards to become established, and the manufacturers haven't really made hard for it yet.
diese Standards, wenn sie nicht implementiert sind.
The standards do not hurt anybody when they are not implemented.
In manchen Fällen ist es halt eben dann einfach, geht dann einfach das Roaming kaputt.
But in some cases the roaming
Dann doch
dies,
faire Sachen zurückgreifen.
and that's why sometimes you have to use proprietary extensions that the other manufacturers haven't done right.
Okay, letzte Frage aus dem Internet.
Final question comes from the internet.
So, die Frage aus dem Internet ist, kann man MIMO-Systeme eigentlich sniffen und bräuchte man da nicht die Channel-Matrix?
The question is, can you sniff MIMO systems and don't you need the channel matrix? And the answer is, yeah, it's a data transmission on layer 1 and you can sniff it.
Muss man natürlich irgendwie gleiche Hardware auf der anderen Seite haben. Das heißt, es wird schwierig irgendwie mit
You need the same hardware on the other side.
Sachen zu sniffen. Da müsste man dann schon einen SDR dafür benutzen.
You would need to use a software-defined radio,
Und auch diese Beamforming-Matrix, dazu braucht man
and the beamforming matrix
weil die Beamforming-Matrix
is not a problem
wird
either.
verwendet, um irgendwie die Aussendung von den Daten her zu verändern, sondern einfach nur von der Richtung
It isn't
her.
used to change data, it's only
Braucht man halt einfach eine
to adjust the
oder man stellt
directionality.
einfach eine Position. Aber dieses Beamforming ist nicht so genau, dass halt eben in die eine Richtung gar keine Daten
Beamforming
gehen,
is
in die
not
andere
so
Richtung.
accurate that all data goes in just one direction. If you have a good enough antenna, you can still listen in.
Okay, danke schön.
Thank you very much. And this concludes our